right? So we say last week we talked about the simple regression, right? So we say we only have one explanatory variable x, and then we have this regression model, right? So we have mu of y equals to beta 0 plus beta 1 x, and then based on the sample, we can fit a line so that we have a equation, right? And then we say in this case, we only have one explanatory variable x, right? Then we call it is the simple regression. But in our real life, simple regression may not be enough to make an accurate prediction for the response variable, right? Then we need to add more explanatory variables into our regression so that we can study about the combined influence of the multiple predictors to the response variable. All right, then we say if we have more than one explanatory variables, then we have the multiple regression. Right, so similar to the simple regression, we say the only difference will be now we not only have one x, we have multiple predictors, we have multiple explanatory variables, we have x1, x2 until xk. So you can add as many as you want, right? So if you think you have 10 factors that will affect the response variable, then you can add 10 variables into your multiple regression. That means this k will be 10, right? So here you have another notation for the k. So the k is the number of predictor variables, or the number of explanatory variables in your regression. All right, okay, so the first one will be the model without the sample. And then once you have the sample, you can fit a multiple regression equation so that we have the detailed value for B0, we have the detailed value for B1, B2 until BK, so that we can use this B0 to estimate beta 0. We can use B1 to estimate beta 1. You use B2 to estimate beta 2 until BK. All right, so just a similar idea, right? So we say mu of y is still the mean value of response variable, right? Beta 0, beta 1, beta k are the unknown regression parameters. We also call them are the coefficients for these variables, right? So that's we say this beta 1 is the coefficient for the variable x1. This beta 2 is the coefficient for the variable x2 until this beta k is the coefficient for the variable xk. Right, so we call them are the coefficients. All right, and then similarly, we still have the two meanings for this y hat, right? So the y hat can be the estimate for the population mean value of y, or this y hat can be just one single prediction of the individual value of y when we plug in the value of x variables. All right, and then similarly, we say we use the B0s until BK to estimate the parameters beta 0, beta 1 until beta k. Right, and then similarly, still have the residuals, which is equals to the observed y minus the predict y. All right, okay. Until here, everything should be very familiar to you. We just add several predictors, several explanatory variables into our regression so that we not only have beta 1, we have beta 2, beta 3 until beta k for each variable we added. All right, so now let's talk about something different. Right. So we say the first topic we want to talk about how you interpret these coefficients. Right. So once you have this equation based on the sample, once you have this equation based on the sample, then how you can interpret B0, how you can interpret B1, B2 until BK. Right. Would that be the same way with how we interpret in the simple regression? Right, so let's look at this example first. Right. So we say when we want to find when we want to buy a house, right? We usually go to the Zillow.com website, right? So we look for a house, and then in the web page of a house, there always be a line tell you what is the estimated price of this house, right? So how they get this estimated price of the house, they just use the multiple regression model. Right, we say if you have a house, the price of the house will be affected by a lot of factors, right? So it will be affected by how many bedrooms do you have, right? How many bathrooms, how many fireplaces, right? How large is this house, right? The living area of this house. How old is this house, right? Where is this house? The location of this house, right? So many factors that will affect the price of the house. All right. And then for this example, I just randomly choose a sample of 1,057 local houses, right? So that means the location will not be our factor anymore, right? So in your module 4 page, you will have this data set, right? So it is called the housing price Zillow, right? So if you open this data set, it will be something like this. All right, so in this data set, we totally have 1,057 houses, right? So we totally have 1,057 observations. All right, and then we say, based on these houses, for each house, I collect the price of this house, the living area of this house, the number of bedrooms of this house, number of bathrooms of this house, number of fireplaces, and the age of this house. All right, and then we say we want to use these factors to make a prediction of the house price. Right, then what you need to do. So you need to first think about the whole process, right? So for personally, right, um, I think the number of bedrooms is more important for me to make the prediction of the house price. Then let's just explore the relationship between the bedroom, number of bedrooms, and the price, right? So I can fit y by x. I can fit a simple regression between the price and the number of bedrooms and see what is the relationship between these two. Right? So this is the scatter plot between the bedrooms and the house price. We say the number of bedrooms will not be continuous random variable, will be the discrete, right? So you can only have 1 bedroom, 2 bedrooms, 3 bedrooms, 4 bedrooms, and 5 bedrooms, right? So it looks like it shows a kind of a linear relationship, right? It's a kind of an increasing trend, right? And then if I fit the line using the jump, and then you will have the output like this. You have the line here, you have this equation, and then the R square is 0.214. All right, so now let's come back to our note. I just make a screenshot of our results. All right, okay, so we say this is the equation, right? And with the R square is 0.214. It's kind of low, right? It is very low R squared. That means we only have 21.4% of the variation in the house price can be explained by the bedrooms, number of bedrooms. All right, so that means maybe the number of bedrooms is not enough to make the accurate prediction for the house price, right? So now, before we think about others, let's think about what does this value mean? This is B0, right? So when we interpret that, that means if a house has no bedrooms, then the house price is predicted to be $14,349. It doesn't have our practical meaning because there's no house with no bedrooms, right? Okay, and then this is B0. Next one, about B1. What does this B1 mean? Is if you have one more bedroom, then the house price will increase by about $50,000, right? Okay, so it makes sense because the more bedrooms, that means the house will be bigger. That means the house will have a higher price, right? So we say the number of bedrooms increase, then the price will also increase because it is positive. All right. Okay, so now we say the number of bedrooms may not be enough for you to make the accurate prediction about the house price. Then we want to consider some other factors. Right? So now let's come back to our data set. Right? Except the bedrooms. I think the living area may be another factor, right? So the living area may have some relationship with the house price. And again, let's just explore the relationship between the living area and the price and see what is their relationship, right? So this is the scatter plot. Looks like a much stronger linear relationship with the house price, right? Okay, and then we say let's fit the line, and then we have this line, and then we have this equation, right? Linear regression equation, and with the living area itself, right? With the R square, which is 0.575. All right. Okay, so this is another simple linear regression with just the living area itself. Right, so we have the R square, which is 0.575, which is much higher than the number of bedrooms. All right, okay, so now we say, what if I combine these two factors together into my regression? What if I can consider the combined influence of the living area and the number of bedrooms? If I can combine them together, there should be much better predictions, right? Okay, and then what I do, we come back to our data set, right? And then we analyze, right? Now we cannot use this fit y by x because in this function, we only have one x. But now I want to include both the number of bedrooms and the living area into my regression. Then I need to use fit model. Right, so this function will allow us to make a multiple regression. Right, so again, here the house price will be the y. Right, and then we say, besides the number of bedrooms, I want to also add the living area into my regression. Right, so now I have number of bedrooms will be my x1, right? And then the living area will be my x2. Right, so now if I run the whole function, this is the default output. Right, you have a lot of plus, right? So let's skip these plus and then go to the end of this output. You have still these three tables, right? You still have the summary of fit table tell you how well does your model fit your sample data, right? You still have your ANOVA table. You still have your parameter estimates table. All right, so let's just focus on the parameter estimates table first. Right, similar to the simple regression, we still have these terms, right? So we have the intercept, that means this line is about beta 0, right? And number of bedrooms, that will be our first variable, first explanatory variable. That means the coefficient will be beta 1, right? And for the second explanatory variable, that means the coefficient will be beta 2, right? So that means the estimate for beta 0, which is B0, will be this much, right? And then next one, B1 will be this much, and then B2 will be 93 something. All right, and then based on this table, we can write this equation, right? So we say the price will be depend on number of bedrooms and living area together, right? So now I put them together, we can see that the coefficients changed, right? So let's make a comparison. We say when we do the linear regression, the simple linear regression with only number of bedrooms, then we have this equation, right? And then we have the B1, which is the coefficient for the number of bedrooms, which is 48,218.91. But now, when I add the living area into the regression, now your coefficients of the bedrooms change to negative 7,487, 83.10. How does that happen? We say if we have the simple linear regression, that means what? That means if the number of bedrooms increases, the price of the house also increase, right? It makes sense because if you have more bedrooms in your house will be bigger, then the house price will increase, right? But now if we have this multiple regression and add the living area into this regression, the coefficient for the bedrooms change to negative. Does that mean that if I have one more bedroom, the house price will decrease by this much? It doesn't make sense, right? We are using the same sample. It just because one is for the simple regression, the other one is for the multiple regression. We just add one more variable into our regression. Why the coefficient changed to negative? Think about it. Right, so now be careful in the multiple regression. When we interpret the coefficients for each variable, we always need to control other variables. We need to make other variables fixed. Right, so now try to understand this negative value here. We say if a house is already with the fixed living area, if the living area of a house is already fixed, it's just a 4,000 square feet, right? And then within this living area, if you have one more bedroom, for example, if your living area is already fixed, you add more bedrooms into this living area. That means you have smaller bedrooms. That means you have very, let's say, empty rooms, right? So that means the design of the house may not be good, right? So in this case, if this value means if your living area of this house is already fixed, then if you have one more bedroom in the house price will decrease by this much. All right. Okay, so now it should make sense now, right? Because if you have a fixed living area, then if you have very smaller bedrooms, but more bedrooms, then the design of the house may not be very good. I will not prefer this kind of house, right? So the house price will decrease by this much, right? So let's just summarize a little bit, right? We say the price tends to increase if the number of bedrooms is the only predictor, right? In our simple regression, right? Then of course more bedrooms means bigger house, means the house price will increase, right? The coefficient of the bedrooms will be positive, right? So now if I add one more variable, which is the living area into this regression, that means I need to consider the living area at the same time, right? So that means the price tends to decrease if the bedrooms increase for fixed living area. More bedrooms means smaller, more cramped rooms, right? So that is why the coefficient for the bedrooms is negative in the multiple regression. Right, so not just add this living area into the multiple regression. Actually, when you add the living area into the regression, we consider the whole effect, the combined effect to the house price. All right, okay, so now that means what? That means for the simple regression, you have the positive coefficient, but for the same sample, but if you add one more variable into this regression, the coefficient can change to negative. The sign of the coefficient may change, right? Change from positive to negative or from negative to positive. The sign can change, but it can also keep the same sign. For example, for the living area in the simple linear regression, right? The coefficient here is positive, but in the multiple regression, it still keep the positive, right? So the sign can be changed, cannot or may not be changed depending on the different cases, right? Okay, so that will be simple regression and the multiple regression, how the different way how you interpret this coefficient. All right, and then to get more idea, I just make up these questions. Let's do these questions together. All right, we say this is the linear regression. We cannot say linear, so multiple regression equation, right? So the first question, identify and explain the meaning of B0. Right, so first identify the B0. So what is B0? The B0 is this value, right? So we say B0 will equals to 28986.10. All right, okay, next, explain what does this value mean? How you interpret this B0? Any volunteer? Anyone want to try? Anyone?
Is that the price of the house when the other variables, bedroom and living area, are zero?
Perfect. Good job, right? So that will be, we say, when a house has no bedrooms, right? That means the number of bedrooms equals to zero, and the living area is 0 square feet. Then the predicted house price is this much, right? So it would be 28986.10. All right. So remember, when we interpret the intercept, we always need to tell whether this interpretation makes sense or doesn't make sense in our real life, right? So does any house has no room and no living area? It is not possible, right? So in this case, we say it doesn't have the practical meaning. All right. Okay, so that will be the interpretation for the B0. All right. So next, what about B1? We say the B1 will be the coefficient for the variable x1, right? So this is x1, this is x2. That means the B1 will be this one, right? So your B1 is negative 7483.10. Now, how you can interpret this negative 7483.10? Let's say,
Oh, is it just the price decreases by that amount, but however many bedrooms increases from zero?
we say one more bedroom, the price will decrease by this much,
Yeah.
right? Okay.
Mhm.
Is that the case? Think about, is that the true case? If you explain this to your customer, does that make sense? If you have more bedroom, the house price will decrease. Let me do an example, right? So we say, now it doesn't make sense because what? Because we have another variable in our multiple regression, right? So now when you interpret this one, that means what? That means we first need to fix the living area. We say when the living area of a house is fixed, then in this living area, if we have one more bedroom, the house price will decrease by this much. All right, now it makes sense, right? So we say when the living area of a house is already fixed, then if we have one more bedroom, the house price will be decreased by this much. Good idea. All right, try one more. Right, so what about B2? We say B2 is the coefficient for x2, right? So which is B2 would be 93.84. Right, how you can interpret this B2? Anyone? Um, Grant, what do you think? Grant?
Hi, could you repeat the question? My Wi-Fi is really bad.
Sure. The B2, we say the coefficient for the living area is 93.84. Then how you can interpret this B2? How you can interpret this 93.84?
Is is that like how much when there's like one living area the price goes up?
Mhm. So that means you say when the living area increase by 1 square feet, the house price will increase by 93.84.
Yeah.
Remember, when we interpret the coefficients in the multiple regression, we always need to control other variables first. right? So that means first we say when the number of bedrooms is fixed, right? We have fixed the number of bedrooms, right? Then if the living area
Increases
increase
by 1 square
by
foot.
1 square foot, and then the
It
house price will
increased by 93.84.
3.84. Perfect. Good job. Thank you. Right, so always remember when you interpret the coefficients in the multiple regression, you have one more thing to do is to control the levels of other variables. All right, okay. Um, just let me make another example, right? So for example, if I add not just the living area, if I add, let's say, the number of bathrooms into my regression. So for example, let's say 82.78 bathrooms. All right, I just made up this number. All right, now how you can interpret this 82.78 then? That means when the number of bedrooms and the living area are both fixed, then if you have one more bathroom, the house price will increase by $82.78. Got the idea? So you always need to control the levels of all other variables, and then now you can focus on your own variable, the one you want to interpret. All right. Okay, so now we kind of done with the interpretations. Let's practice for other questions. Right, so the next one, number 4. A house with 4 bedrooms with 4,700 square feet of living area. What is the predicted price for this house? How you can calculate the predicted price? You see the price predicted will equals to, we just plug in 4 bedrooms into the equation and then plug in the 4,700 into the living area, right? So that we have 28986.10 minus 7483.10 times 4 bedrooms, and then plus this 93.84 times totally 4,700 square feet for the living area, and then you can calculate as 440,000 and $101.7. Right, then we say this is the predicted house price for this 4 bedroom and 4,700 square feet of the living area house. All right, next question. In fact, this house would sell for $450,000. Right, find the residual. Again, how you can find the residual? The residual equals to the observed value minus the predicted value, right? So what is the observed value? What is the observed y? Ben?
The observed is 450,000.
Okay. What is the predicted?
Um, is it that 440,101?
Perfect. All right, so that would be what we observe and the predict, right? So it would be 440101.7, and then we have the residual, which is $9898.3. Okay, so this is our residual. Last question. What does this residual say about the price of this house? Try to make a discussion. What does this residual say? Julia.
That the house is more expensive than we predicted.
Perfect, right? So that means for the house buyer, it is a bad deal, right? Because the house buyer paid much more, which is about $10,000 more than what we expect, right? But of course, for the seller, it's a good news, right? So they earned a lot more than expected. All right. Any question until now? Any questions about the interpretations? Remember, there is a difference. Hear me now? Yes.
Yes.
Okay. Thank you. All right. So we say all about these are based on when our regression is done by the jump, right? When our regression is meaningful, right? So we say for the simple regression, right? We say even though you have two variables that they are not related, right? So for example, if I have a variable is called, let's say the hours you spend for ISA 225 weekly, right? The other variable y is, let's say, the house price. Right, so we say there is even no relationship between these two, right? So, but if I have a data set, I have a house price data set, a house price column, and another column is for the hours you study for ISA 225. Then, whenever you put these two columns data value into the jump can always produce an equation out. Right? Even though they don't make any sense, even though there's no relationship between these two, but jump cannot figure out whether there is any relationship, right? They just produce the scatter plot and then get the line, and then you need to decide. For the simple regression, we always need to decide whether beta 1 equals 0, beta 1 not equals 0 to say whether this linear regression is meaningful or not meaningful, right? So actually we say if beta 1 is 0, then the whole part for the x doesn't make is just a 0. That means the x will not affect y. That means the whole regression is not meaningful. Right? Okay, so now we have a multiple regression. We have x1, x2, x until xk in our regression. Right? So let's say in our multiple regression, we have the model which is mu of y equals to right. So the mu of y equals to beta 0 plus beta 1 x1 plus beta 2 x2 until as many as you want, beta k sk, right? So this is our model, multiple regression model. All right. Okay, so now we want to know whether the overall multiple regression is meaningful or not meaningful. Right? We want to test the overall significance of the regression model. I want to know whether the whole regression, multiple regression model is meaningful or not meaningful. That means, what do we need to test? We want to test whether the whole part for the explanatory variable is equals to 0 or not, right? So if we say if beta 1 is 0, beta 2 is also 0, and all of these coefficients are all zeros, then there is no relationship between any explanatory variable with this response variable. Right, so that means there is no need for us to make the multiple regression. That means this multiple regression is actually not meaningful. You don't need to do anything else because it's just not meaningful, right? So this is the null hypothesis, right? So we want to test the overall significance of the regression model. We want to make sure, we want to check whether all of these coefficients are just equals to 0. No relationship between any of the explanatory variable with the response variable. Right. Now let's think about the alternative hypothesis. That means alternative hypothesis will be the multiple regression makes sense. The multiple regression is meaningful, right? Okay. Do we need to make sure that beta 1 is not 0, and beta 2 is not 0, and beta 3 is also not 0, and all of these betas are not 0? Do we need to check this? Do we need to make sure all of them are not 0 to make sure the regression is meaningful? Maybe beta 1 is 0, beta 2 is 0, but beta 3 is not 0. Then the whole regression is still meaningful. There is some explanatory variable have the relationship with the response variable, right? That means the whole regression will be meaningful. Okay, so in this case, we don't need to check all of these betas are not 0. We just need to check at least one of them is not 0. Then the whole multiple regression will make sense. All right, so that would be our alternative hypothesis, which is at least one of them is not 0. I don't care which one is not 0, but at least one should not be 0. All right, so that would be our hypothesis, right? So the hypothesis for the overall significance of the regression model, right? And then for this kind of hypothesis test, we will learn about another test. We call it is the F test. Right? We say for the simple regression model, we just test we use the t-test to test the beta 1, whether beta 1 equals 0 or not, right? But for the multiple regression, we use the f-test to test the overall significance of the regression model, right? So before we go to the next step, before we go through the f-test statistics, we have something else, right, to talk about first. All right, so we need to introduce several notations. Right, the first one is the SSE. Right, so what is SSE? SSE has the formula which is the sum of E squared. What is E? E is the notation for the residual, right? So you residual squared and then sum of all the residuals together, then we call it is the sum of squared residuals, or we call this residual as just the error, right? And then this one is short for SSE. Right, so this is the first one. The SSE is the sum of squared residuals, right? And next one is called SSR. So what is SSR? SSR is the sum of squared for the regression. All right, and then one more, SST is the total sum of squares. Right, here are the formulas. I will not ask you to calculate these formulas. Just need you know what is the SSE, what is SSR, what is SST. Right, so all of these three are the sum of squares. Right, we say the SSE is the sum of square for the error, for the sampling error. All right, and SSR is for the regression, the sum of square for the regression. And then we have one more SS, which is the SST, which is for the total. Right, and then we have the relationship. We say the SSE plus this SSR will equals to the SS total. So what are these sum of squares? Actually, these sum of squares will tell you the variance of y, the variation in y, right? So we have a total variation in y, and as what we explained in the simple regression, right? So we say, what is r square? The r square is the proportion of the observed variation in y that can be accounted by the regression, right? Okay, so we say the observed variation in y can be divided into two kinds. One kind is because of the regression. The other kind is because of the sampling error, right? So now we combine these two variations together, then you have the total variation in y. So that we call it is SST. All right, so now we got the relationship SSE plus SSR equals to SST. All right, and then these three sum of squares has their own degree of freedom. All right, so let's talk about SST. Right, so SST has the degree of freedom is just n minus 1. The total sample size, the total number of observations in your sample. The sample size minus 1, n minus 1 will be the degree of freedom for SST. All right, so it will be the total variations in y. So that means how many y's do you have? You totally have n sample size y values, right? And then minus 1 will be the degree of freedom. Right, so next one, SSR. SSR is the sum of squares for the regression. Now, in the regression, what do we need to care about? We care about how many explanatory variables in our multiple regression, right? How many axes? So that we have x1, x2 until xk. So that means you totally have k variables, k explanatory variables in the multiple regression. Then the degree of freedom of SSR will be k. All right, and then we say for SSE, the degree of freedom, how we can get this degree of freedom? We say the relationship is SSE plus SSR equals to SST. Same thing for the degree of freedom. The degree of freedom for SSE plus the degree of freedom for SSR will equals to the degree of freedom for SST. So that means n minus 1 minus k will be this degree of freedom for SSE. So the SSE have the degree of freedom n minus k minus 1. All right, so now we say we have the relationship SSE plus SSR equals to SST. And now, if I use the SSE, which is the sum of squared, divide by how many of them? The degree of freedom n minus k minus 1. And then we call this is kind of sum of the squared divided by how many of them we kind of get the mean, right? We get the average, and then we call this is the mean squared error. Are you familiar with that? MSE, right? So this is the mean squared error, which is MSE. All right, next one, SSR, which is the sum of squared regression divided by the degree of freedom, which is K. Then we call this as the mean squared regression, MSR. All right, and then what is the F-test statistics? The F-test statistics will equals to MSR divided by MSE. All right, so this is the F-test statistics. It equals to MSR divided by MSE. MSR is the SSR divided by the degree of freedom K. MSE is the SSE divided by the degree of freedom N minus K minus 1. All right, so since the F-test statistics is based on a fraction between these two mean squared regression with the mean squared error, then the F-test statistics has 2 degree of freedoms. Right, we call it is the degree of freedom 1 and degree of freedom 2. Degree of freedom 1 is the degree of freedom for the top, which is the numerator degree of freedom. Right, degree of freedom 2 will be the degree of freedom in the bottom, which is the denominator degree of freedom. Right, so for the F-test statistics, we have 2 degree of freedoms, and then we can write as like this: F of the first degree of freedom K, the second degree of freedom N minus K minus 1. Right, so we have 2 degree of freedoms for the F-test statistics. All right, so now we all focus on the theoretical things, right? So kind of not easy for us to remember all of these, right? So now let's focus on our outputs, right? So we say in our regression output, right? So in our regression about with the number of bedrooms and the living area, right? The first table is about the summary of fit, will tell us how well is your model, right? The last table is about what is your detailed estimates and their standard errors, right? And then the t-test statistics for each parameter, for each coefficient. Right, the middle one, we call it is the ANOVA table. We didn't talk about this ANOVA table in the simple regression because it is not very useful, but for the multiple regression, it is very useful, right? So we call it is ANOVA table. ANOVA table is short for the analysis of variance. So here, the variance of the y. Right, so again, we say the variation in y can be divided into 2 sources, right? So either from the model or from the sampling error, right? So the model, we can also call it is because of the regression, right? And then one more source of the variance is the sampling error. And then you have the total variance of y as the last line. All right, and then let's look at the first column, the degree of freedom. All right, so we say the first one, the degree of freedom for the regression, right? So just to think about the degree of freedom for the regression should be how many explanatory variables in our regression, in our multiple regression, right? So the degree of freedom should be K. In our example, we include the living area, and the number of bedrooms, right? So we totally have two variables, two explanatory variables, right? So that means our k just equals to 2, which is the degree of freedom for our regression. All right, and then next, the degree of freedom for the air. What is the degree of freedom for the air? Would be this one. Would be this one, right? For the air, which is n minus k minus 1. So that means we totally have n equals to 1057, right? So n minus k minus 1 would be 1057 minus k, which is 2, minus 1 will be 1054. So this is where does this 1054 come from? So it is the degree of freedom for the air, which is n minus k minus 1. Right, the last one, the degree of freedom for the total will be n minus 1. Right, so which is 1057 minus 1, which is 1056. Right, now you can see the relationship, right? So we say the degree of freedom for the regression plus the degree of freedom for the air will be the degree of freedom for the total, right? 2 plus 1054 will be 1056. All right. Okay, so next column will be the sum of squares. Right? Okay, so what are these values? The first one, it is sum of squares. So of course it is SS something, right? So this is SS for the regression, right? So that will be SSR, right? So next one, 2.64 65 with the 10 with power 12, right? So this one will be the SS for the air, right? So it will be SSE, right? The last one will be sum of squares for the total, right? So that will be SST. All right, one more column. Next column is the mean square column, right? So that means the first one is mean square of the regression. Next one, mean square of the air, MSE. All right. Okay, so now we have MSR and MSE, our F ratio, which is our F test statistics, which is just the MSR divided by MSE, will be this 723.23. Right, so this will be our F test statistics, comes with the corresponding p-value. All right, so you need to know the relationship between these entries. You need to know where does these entries come from, right? So for example, if I gave you the sum of squares here, right? You need to know how you get this mean square, right? You need to understand the relationship, right? And then we say once we have the F test statistics and then the corresponding p-value, then everything come back to our hypothesis test, right? So we say if your p-value is very small, then less than the alpha, that means we reject the null hypothesis. That means we have enough evidence to support that the multiple regression is meaningful. Right? But the other way, if your hypothesis test, if your p-value is larger than the significance level, if your p-value is large, then that means we fail to reject the null hypothesis. that means your multiple regression is even not meaningful. That means you can just stop here. You don't need to do any other hypothesis test. You don't need to do any other confidence intervals or any other interpretations, because your whole multiple regression just don't make any sense. So you can just stop here if you fail to reject the null hypothesis. All right. Okay, so that will be all for the first hypothesis test in the multiple choice multiple regression, right? The overall significance of the multiple regression, right? So let's just spend the last 1 more minute, right? So review a little bit. We say we have SSE, SSR, SST, right? We have the relationship. We say SSE plus SSR equals to SST. Right? SSE is about the air. We have the degree of freedom, which is n minus k minus 1. Right? SSR is about the regression. It has the degree of freedom is k. SST is about the total. We have the degree of freedom is n minus 1. Right? So again, the degree of freedom for the error plus the degree of freedom for the regression will be equals to the degree of freedom for the total. Right? And then if we use the sum of squares divided by its own degree of freedom, we have the mean squares. Right? So we have the mean square error, mean square regression, and then we use the mean square regression divided by mean square of error. We get the F-test statistics with these 2 degree of freedoms, right? And then once we have this F-test statistics, we have their corresponding p-value, and then we can use this p-value to determine whether this overall multiple regression is meaningful or not meaningful. If this regression is meaningful, then you can continue to test other things. If your multiple regression is not meaningful, then you can just stop here. You don't need to do anything else. Right, got the idea? All right, okay, that will be all for today. And